When you activate a torch, you believe you comprehend what's occurring. Illumination departs the torch. It traverses space and it strikes the surface. Straightforward, correct? The illumination transferred from here to there. Yet that's not what's genuinely occurring. That's merely a narrative we construct for ourselves because our brains develop to comprehend objects like stones and spheres, not photons. Here's the complication. We're constrained with terms like transfers and traverses and proceeds from point A to point B, yet these terms derive from our experience with conventional objects. A sphere transfers, you can observe it. At each moment, you could theoretically observe its location. It possesses a trajectory. Yet illumination, a photon, it doesn't function that way whatsoever. Allow me to inform you about an experiment. Actually, it's the experiment, the double slit experiment. You've likely encountered it, yet allow me to explain what it genuinely signifies. You obtain a source that emits photons individually. You position a barrier with two openings in it, and you position a detector on the opposite side. Now, here's the inquiry. Which opening does the photon traverse? And the response is, it traverses neither opening, and it doesn't traverse both openings. The inquiry itself is incorrect. You understand, we want to ask what trajectory the photon followed, yet nature doesn't address that inquiry. Nature doesn't concern itself with that inquiry. The photon doesn't possess a trajectory the way a sphere possesses a trajectory. Now I must be extremely precise here. I still catch myself stating things like, wait, well, it traverses this opening or that opening. Yet when I state that, I must maintain awareness of what I genuinely intend. I intend in the sense of combining amplitudes. The photon possesses an amplitude to proceed one way and an amplitude to proceed the other way. And if these amplitudes oppose each other, the illumination won't arrive there even though both openings are accessible. Allow me to step back and explain what we can actually compute. We can compute the probability that a photon detected at point A will subsequently be detected at point B. That's something we can measure. That's something nature informs us. Yet notice what I expressed. Detected at A, then detected at B. I didn't express it transferred from A to B. I expressed we detected it twice. And here's the elegant, peculiar aspect. To compute that probability, we employ this method that I developed. You take every conceivable trajectory from A to B, and I mean every conceivable trajectory. Straight trajectories, curved trajectories that travel to the moon and return, trajectories that loop around 17 times, every single conceivable trajectory. And you assign each trajectory a small arrow, a small complex number whose angle depends on how much time that trajectory requires. Now, individuals learned about this and they became extremely enthusiastic. They expressed, aha, the photon takes every trajectory, and they began imagining photons separating and proceeding everywhere simultaneously and then reuniting. Yet that's not what I expressed. That's not what the mathematics indicates. I never expressed the photon takes every trajectory. I expressed to compute the probability you must consider every trajectory. You understand there's a significant distinction between stating the photon takes all these trajectories and stating to compute where the photon might be detected, employ some amplitudes over all conceivable trajectories. The initial one attempts to inform you what the photon is doing when you're not observing it. The second one merely informs you how to compute what you'll observe when you do observe. And that's the matter. Quantum mechanics doesn't inform you what occurs when you're not observing. It only informs you what you'll discover when you do observe. And when you attempt to observe, when you attempt to determine which trajectory the photon followed, you alter the experiment. You eliminate the interference pattern. You alter what occurs. Allow me to provide another illustration. Suppose I have two electrons that will scatter off each other. In the traditional classical representation, they approach each other. They repel because both possess negative charge and they separate. Straightforward. A force exists between them. Yet what causes that force? Well, we developed this elegant theory, quantum electrodynamics. And in this theory, we state that the electrons exchange a virtual photon. One electron emits a photon, the other one absorbs it, and that's how they push each other apart. And we sketch these diagrams, these Feynman diagrams with lines representing the electrons and a wiggly line representing the photon. And everyone's satisfied. Yet here's what's troubling some individuals. They examine that diagram and they inquire, okay, so when did the photon get emitted? Where did it proceed? How rapidly was it transferring? What was its trajectory? And the response is Those aren't the appropriate inquiries. The diagram isn't a depiction of what occurred, it's a tool for computing what you'll measure. That virtual photon in my diagram, it doesn't obey the standard relationship between energy and momentum that real photons obey. It's off-mass shell, as we express. It can carry the incorrect energy. It can even transfer faster than light in a sense, yet you can never detect it transferring faster than light because you can never detect it at all. It's virtual. It's part of the computation, not part of what you can measure. Now I want to inform you about something even stranger. That virtual photon that I just informed you about, it doesn't possess a definite position. It's described by a wave that occupies all of space. A plane wave, we designate it. It's everywhere simultaneously. So when I sketch that wiggly line in my diagram connecting one electron to the other, that's not showing you the trajectory of the photon. That line merely represents a mathematical expression, a propagator that informs you how to compute the amplitude for this interaction. The photon didn't transfer from one electron to the other. It was in some sense everywhere in space and both electrons interacted with it. Or you could state both electrons generated a disturbance in the electromagnetic field, and that disturbance is what we're computing. The language doesn't really matter as long as you employ the appropriate mathematics. Allow me to attempt to make this clearer. When I state a photon transfers from A to B, what I genuinely intend is this. An amplitude exists for a photon to be detected at A at time 1, and an amplitude exists for a photon to be detected at B at time 2, and a formula exists for computing that combined amplitude. That formula involves summing over all the ways this could occur, all the conceivable trajectories. Yet those trajectories aren't real trajectories. They're mathematical tools. You might state, okay, acceptable. Yet the photon must be somewhere between when I detect it at A and when I detect it at B. And I must inform you, quantum mechanics doesn't provide you an answer to that inquiry. It's not that we don't understand the answer, it's that the inquiry doesn't possess an answer. In quantum mechanics, allow me to express it another way. In quantum mechanics, particles are described by wave functions. The wave function informs you the probability amplitude for locating the particle at different places if you observe. Yet if you're not observing, the particle doesn't possess a position. It's not that it possesses a position and we don't understand what it is. It's that position isn't a property the particle possesses until you measure it. Now, some individuals don't appreciate this. They want to state, no, the photon must genuinely be somewhere. It must genuinely be doing something. And they attempt to construct different interpretations of quantum mechanics, where particles possess definite positions constantly. And that's acceptable. You can do that, yet you must add supplementary elements to the theory, hidden variables, or parallel universes, or pilot waves, or something. And none of that alters what we can actually measure. The quantum mechanics we possess, the theory we employ to generate predictions, doesn't inform you where the photon is when you're not observing, and it doesn't need to. It predicts everything we can actually measure with incredible accuracy. Here's another aspect. Individual state illumination transfers at light speed. Well, yes and no. I mean, when you measure light speed, you obtain this number, approximately 300,000 kilometers slice s. That's what you measure. Yet in the quantum theory, when we compute the amplitude for a photon to proceed from A to B, contributions exist from trajectories that transfer faster than that and contributions from trajectories that transfer slower than that. Now, over extensive distances, these faster and slower contributions cancel out, and what remains is the standard light speed. Yet over extremely short distances, these other possibilities matter. They're not merely mathematical tricks. They possess real physical effects. They alter atomic behavior. They affect energy levels. We can measure these effects. So what does it signify to state illumination transfers at light speed? It signifies that's what you measure when you measure it. Yet the underlying quantum amplitude involves all these other possibilities as well. Allow me to inform you about something else that troubles individuals. They state, okay, I comprehend that we cannot understand the exact trajectory of a photon, yet surely the photon is propagating through space somehow. Surely it's transferring even if we cannot track it exactly. Yet that's still thinking classically. That's still imagining the photon as a small ball that possesses a position at every moment. In quantum field theory, which is the appropriate way to consider photons, a photon particle that's transferring through space doesn't exist. A disturbance exists in the electromagnetic field. And that disturbance doesn't possess a definite location similarly to how a ball does. It's spread out. It possesses an amplitude to affect things here and an amplitude to affect things there, and these amplitudes to interfere with each other. When you detect a photon, what you're genuinely detecting is a quantum of energy being absorbed from the electromagnetic field. The field was in an excited state, and after the detection, it's in a lower energy state. And your detector has absorbed that quantum of energy. Yet that doesn't signify a small particle existed that transferred from the source to the detector. Now I understand what you're thinking. You're thinking, this is irrational. Illumination obviously transfers. I can observe it transferring. When I activate a torch, the illumination reaches the surface after a certain time. If I'm sufficiently distant, I can even measure how long it requires. And you're correct. You can measure these things, yet what you're measuring is the duration between when photons begin being emitted and when they begin being detected. You're not tracking the motion of individual photons. Allow me to provide an analogy, though I must caution that all analogies fail. Envision you're seated on a shoreline observing waves. You can observe a wave crest transferred toward the shore. You can measure its speed, yet what's actually transferring? The water isn't transferring forward with the wave. The water is merely ascending and descending. It's the pattern that's transferring, not the substance. Now that analogy fails in many ways because illumination isn't composed of substance that's waving up and down. And I'm not stating illumination as merely a wave. Yet the point is that movement can be a more subtle concept than we typically consider. What we designate the motion of illumination might be more similar to the propagation of a pattern than the movement of an object. Here's something I consider elegant. When we perform quantum electrodynamics, when we compute how illumination and matter interact, we don't need to express what the photon is doing between interactions. We merely compute the amplitude for different interactions to occur. An electron emits a photon, another electron absorbs a photon, and we compute the amplitude for that. We don't need to track the photon in between, and it functions. Remarkably, it functions. Quantum electrodynamics represents the most accurate theory in all of physics. We can compute phenomena like the magnetic moment of the electron to 10 decimal places, and it aligns with experiment. No other theory approaches that kind of precision. So whatever illumination is doing, whatever it signifies to express a photon transfers, the mathematics we're employing to compute it is absolutely correct. Now allow me to address something directly. You might express you're merely playing word games. Obviously, illumination transfers in some sense. Obviously, something occurs between when illumination is emitted and when it's detected. And okay, yes, something occurs. The electromagnetic field alters state. The wave function evolves. Designate it movement if you want. Yet it's not movement like a ball moving. It's not movement where the photon possesses a definite position at each instant and follows a definite trajectory. The title of this talk expresses illumination doesn't transfer. And what I intend is this. If by transfer you intend what a ball does possessing a definite position that changes continuously along a trajectory, then no, illumination doesn't transfer. Illumination performs something much stranger. Allow me to inform you about one more aspect, and this is something I consider genuinely important. When you attempt to observe which trajectory a photon takes, when you attempt to capture it in the act of transferring, you alter what occurs. You eliminate the interference pattern. The act of observing the trajectory makes the photon behave differently. It's not similar to the photon was following a definite trajectory and you merely disturbed it slightly. It's that the trajectory doesn't exist until you measure it. And when you do measure it, you obtain an answer. Yet you've altered the experiment into a different type of experiment. This is what Heisenberg was conveying with his uncertainty principle. You cannot understand both where something is and where it's proceeding, and it's not merely that you cannot understand it, it's that the thing doesn't possess both properties simultaneously. If it possesses a definite position, it doesn't possess a definite momentum. If it possesses a definite momentum, it doesn't possess a definite position. For a photon, it's even more extreme. A photon with a definite momentum, like what we designate a plane wave, is spread out over all of space. It doesn't possess a position at all. And a photon that's localized to a small region, well, that's composed of a superposition of photons with many different momenta. You cannot have it both ways. So when you ask where is the photon as it transfers from A to B, you're asking an inquiry that assumes the photon possesses a position at each instant, yet it doesn't, not in the quantum mechanical description. The wave function provides you amplitudes for where you might locate it if you observe, yet until you observe, it doesn't possess a position. Now, I want to be explicit about something. I'm not stating photons aren't real. They're extremely real. We detect them constantly. What I'm stating is that they're not real in the way we imagine everyday objects are real. They don't possess the properties we consider they should possess. They don't transfer along trajectories. They don't possess positions when we're not observing them. And this isn't merely philosophy. This possesses practical consequences. The fact that photons behave this way is why lasers function. It's why photosynthesis functions. It's why the sun illuminates. It's why you can observe anything at all. The strange quantum behavior of illumination is essential to everything. You know what's amusing? Newton considered illumination was composed of particles. Then Young performed his double-slit experiment and demonstrated illumination was a wave. Then Einstein appeared with a photoelectric effect and demonstrated illumination was particles again. And then we developed quantum mechanics and recognized illumination is neither particles nor waves, or it's both, depending on how you observe it. Yet here's the genuine answer. Illumination is illumination. It's not comparable to anything else. It behaves similarly to waves in some experiments and similarly to particles in other experiments, yet it's not genuinely either one. It's something that doesn't possess a name in everyday language because we don't experience anything comparable to it in everyday life. We're constrained employing words like particle and wave and transfer because those are the words we possess, yet none of them quite align. The mathematics aligns, the equations function, yet the words are always slightly incorrect. Allow me to conclude with this. You inquired why illumination doesn't transfer, and I hope I've provided you some sense of what I intend by that. Illumination doesn't transfer the way you consider it transfers. It doesn't follow a trajectory. It doesn't possess a position between measurements. What it does is much stranger and much more elegant than simple movement. The photon is described by an amplitude, a complex number that informs you the probability for different things to occur. That amplitude evolves according to an equation, Schrödinger's equation. And when you perform a measurement, when you detect the photon, that amplitude collapses to provide you a definite result. Yet between measurements, the photon doesn't transfer. It doesn't remain stationary either. It exists in a superposition of possibilities. And that superposition evolves in a way that we can compute, yet that doesn't correspond to anything transferring along a trajectory. This is quantum mechanics. This is how nature functions at the smallest scales, and I understand it sounds irrational. It sounds like I'm fabricating it, yet I'm not. This is what the experiments demonstrate. This is what the mathematics describes, and it functions. Nature doesn't concern itself with what we consider should occur. Nature doesn't concern itself with our intuitions. Nature merely performs what it performs, and our responsibility is to determine the rules. And the rules express that illumination doesn't transfer the way we considered it transferred. It performs something much stranger and much more remarkable.